Noir plasma chrome bleed. Unlocking knowledge, inspiring innovation, empowering curious minds.
This website makes learning so easy. I found all my resources here.
Like what you share.
Okay, let's jump right into this explainer. Today, we're taking a grand tour of how we mathematically construct the physical universe. We'll be starting all the way down with a single lonely electron and scaling up step by step to macroscopic quantum matter. It's a massive, incredibly ambitious physical challenge, and honestly, a completely fascinating journey of building complexity. Let's dive in. So, think about this. How do you actually get from one tiny, single particle to an entire massive quantum state? Well, that's exactly the core question we're answering today. By mapping out the theoretical hierarchy of atomic, molecular, and optical physics, which physicists just call AMO physics for short, we're going to show you exactly how we scale up these concepts and overcome some absolutely mind-bending complexity at every single level. Here is our working blueprint for the physical universe. We'll be looking at the foundation of atoms, managing many electrons, fields, structure, and QED, building molecular structures, probing matter with spectroscopy, and finally, macroscopic quantum frontiers. Right, let's get started. Section 1, the foundation of atoms, starting with a single electron benchmark. To build a universe, you have to start with a rock-solid baseline, right? Ours is a simple single-electron hadronic system. At this level, the energy is perfectly solved by the time-independent Schrödinger equation. Beautiful, elegant math. But the real universe is messy and demands relativistic corrections. We have to add kinetic corrections, spin-orbit coupling, and my personal favorite, the Darwin term. That Darwin term describes this incredibly rapid quantum jitter, literally called Zitterbewegung, which means trembling motion in German. It physically smears the electron's position and softens the pull of the nucleus. It's just wild how much nuance exists inside just one single atom. Moving on to Section 2, managing many electrons, and the complexity roadblock. Okay, so here's where it gets tricky. The second we add just one more electron to make helium, our perfectly solvable model shatters into an analytically insoluble three-body problem. It's crazy that adding just one piece totally breaks the perfect math. This whole new level of complexity is governed by the Pauli exclusion principle. It dictates that total wave functions absolutely must be anti-symmetric under particle exchange. Physically, this forces our helium into distinct uncoupled energy states. You've got perihelium, which is a spin singlet, and orthohelium, a spin triplet, with antisymmetric wave functions that actually end up sitting lower in energy. So, how do we scale up beyond helium to atoms with dozens of electrons? Well, physicists have to use some incredibly ingenious approximations. First up is the central field approximation, which essentially just averages out the repulsion. Then there's the Thomas Fermi model. This one is a bit of a head trip because it treats the electrons purely statistically. It's almost like looking at a massive crowd of people confined in a room, rather than tracking individual people. But for true, hard precision, we use the Hartree-Fock method. This relies on a Slater determinant to respect that tricky Pauli principle, and then iteratively crunches the math until the predicted electrical fields are completely, perfectly self-consistent. Now, think of this next part as a cosmic tug-of-war that actually changes depending on the sheer physical size of the atom. In lighter atoms, we use what's called LS coupling. That's because electrostatic forces win the battle here, meaning orbital and spin momenta kind of just couple independently. But as atoms get heavier and heavier, those internal magnetic spin-orbit fields become so massive that they completely take over. They win the tug-of-war. This forces physicists to switch tactics entirely to JJ coupling, where individual total angular momenta couple directly to each other. When we're trying to figure out the ground state energy in LS coupling, we lean on Hund's rules to mathematically minimize all that intense Coulomb repulsion between the electrons. A really great way to visualize this is to think of electrons like passengers getting onto an empty bus. You know how people are. They will always try to sit in empty rows by themselves to maximize their total spin, long before they ever start pairing up in seats. They do this purely to avoid that repulsive interaction. Section 3. Fields, Structure, and QED. Let's look at external interactions and nuance. So atoms don't just sit in isolated mathematical perfection. When they actually interact with the messy reality of external fields, their energy levels fracture and split apart. Magnetic fields literally torque the atom's magnetic moment to cause Zeeman splitting. Electric fields cause Stark shifts. But hey, even without the outside world interfering, the nucleus itself creates incredible nuance. The nuclear spin interacts with the electrons to create these incredibly tiny hyperfine structures, and even just the sheer mass and volume of different isotopes will noticeably shift the spectral lines we observe. And this brings us to a concept that reveals exactly why all this extreme nuance matters so much: the Lamb shift. Explained by quantum electrodynamics, or QED, this proves that empty space isn't, well, actually empty. It shows us that zero-point electromagnetic fluctuations in the vacuum literally jiggle the bound electron. This stochastic oscillation lifts the degeneracy of very specific hydrogen states. It leans right into the spooky, mind-bending nature of quantum physics, proving for sure that the vacuum of space is alive with fluctuating energy. Okay, Section 4, Building Molecular Structures. Time to scale up to molecules. As we scale up from single atoms to actual molecules, we run into a massive physical mismatch. See, nuclei are thousands of times heavier than incredibly fast electrons. It is literally like comparing an elephant to a fruit fly. So we solve this profound mismatch with a brilliant shortcut, the Born-Oppenheimer approximation. Because the electrons zip around so incredibly fast, we can essentially treat the lumbering nuclei as if they are perfectly stationary. We completely decouple them mathematically and then just solve for the electronic energies on their own. Once they're decoupled, we can build molecular orbitals simply by taking a linear combination of atomic orbitals. But what happens when a molecule absorbs energy? For that, we rely on the Frank-Condon principle. Think about this for a second. Electronic transitions happen in mere femtoseconds. That is so outrageously fast that time practically stands still for the much heavier nuclei. Because the nuclei literally don't have time to move during the electron's jump, these transitions are considered strictly vertical on an energy diagram, so they become entirely dependent on the spatial overlap of the vibrational wave functions. Moving on to Section 5, Probing Matter with Spectroscopy, which is essentially our observational toolkit. Now, you might be wondering, how do we actually know all this microscopic math is real? Simple. We observe it directly. This toolkit is exactly how we identify mysterious chemicals in a lab, or figure out what elements are burning in galaxies billions of light years away. Microwaves cause rigid molecules to physically tumble end over end. Infrared light perfectly matches the fundamental vibrational modes of chemical bonds. Radio frequencies gracefully flip nuclear spins, which, by the way, is the exact basis for MRI machines. Every specific type of electromagnetic energy triggers a beautifully specific, predictable physical mechanism. And finally, Section 6, Macroscopic Quantum Frontiers. We're looking at the extremes of matter. For our final scale-up, we are taking this finely tuned quantum blueprint we've built to the absolute extremes of physical conditions. I'm talking about the fastest speeds and the coldest temperatures imaginable. This number here is a femtosecond, 10 to the negative 15 seconds. To put that completely wild number into perspective for you, a single femtosecond is to 1 second what 1 second is to over 31 million years. Using femtosecond pump probe spectroscopy, physicists fire off ultra-short laser pulses to capture real-time, freeze-frame snapshots of nuclear dynamics. We are quite literally tracking chemical reactions as they happen. On the flip side, we can also use lasers to essentially stall matter entirely through laser cooling. Now, wait a minute. How does hitting something with light make it stop? Well, imagine you're throwing ping pong balls, those are our photons, at a rolling bowling ball, the atom. If you hit it with enough ping pong balls perfectly from the opposite direction, it's eventually going to slow to a halt. By blasting atoms with precisely tuned lasers inside a magneto-optical trap, we use that photon momentum to cool atoms down to staggering microkelvin temperatures. And if you manage to cool those trapped atoms down just a tiny fraction more, things get weird. Something magical occurs. Their fundamental quantum wave nature actually begins to expand. Soon enough, the individual atoms literally overlap, completely merging and losing their individual identities. They condense into a single macroscopic quantum entity called a Bose-Einstein condensate. This giant superatom structure is governed by a mean field math called the Gross-Pitovsky equation. And there it is. We've successfully made the climb. We started with the theoretical simplicity of a single hydrogen electron, fought our way through the incredible, messy complexities of multi-electron molecules and external fields, and traveled all the way up to engineering macroscopic, ultra-cold quantum matter. It is an absolutely brilliant framework, but it does leave us with a thrilling, almost spooky thought to ponder. As our experimental tools continue to get faster and colder, what entirely new rules for the quantum blueprint are just waiting out there in the dark for us to find them? Take a moment to let that sink in. Thanks for joining me on this explainer, and we'll see you next time.
Like what you shared.
This website makes learning so easy. I found all my resources here.
Noir plasma chrome bleed. Unlocking knowledge, inspiring innovation, empowering curious minds.